Now we define order or natural order on the set of natural numbers. We say that m is less than or equal to n if there exists a natural number k such that m plus k equals n. For example, 3 is less than or equal to 7 because 3 plus 4 equals 7. We also say that 7 is greater than or equal to 3. Next, we talk about the reflexive property. This means every natural number m is less than or equal to m. It is obvious from the definition, because m plus 0 equals m for every natural number m. Next is the antisymmetric property of the order. It says that if m is less than or equal to n, and n is less than or equal to m, then m equals n. Two different numbers m and n should not have the same order or relation simultaneously. If one happens, the other does not. That is, the relation is antisymmetric. Lastly, we have the transitive property of the order on the set of natural numbers. It says if m is less than or equal to n, and n is less than or equal to p, then the relation or the order is transitive, which means m is less than or equal to p. From the definition, there are natural numbers k1 and k2 such that m plus k1 plus k2 equals p. The set of natural numbers, together with the order and its three properties, namely reflexive, transitive, and antisymmetric, makes it a partially ordered set. Indeed, we will see, in due course of time, that it is a totally ordered set. Law of trichotomy is a fundamental order property of natural numbers. It says, for any two natural numbers m and n, either m is less than n, or m equals n, or n is less than m. It is guaranteed that one of them will be true. We say that m is less than or strictly less than n if m plus k equals n, k is not 0, or m is not equal to n. We shall prove the law by using the principle of mathematical induction on m. First, the base case, then the induction hypothesis for m, and lastly proving the proposition for s of m, or m plus 1. If m equals 0, then for any natural number n, that is, if n equals 0, we have m equals n, the proposition holds in this case. If n is not equal to 0, then 0 plus n equals n, that is, 0 less than n, a true statement. N less than 0 is impossible, because n plus k is not equal to 0 for any non-zero n, and for any natural number k. So the proposition holds true for m equals 0, and for any natural number n. Next, assume that the proposition is true for m and for any n. We shall prove that the proposition holds true for s of m, or successor of m, or m plus 1. We need to show exactly one of the following is true. So we consider and analyze the three possibilities in separate cases, that is, case 1, case 2, and case 3. In case 1, that is, the induction hypothesis is such that n is less than m. Then it is obvious that n is less than m, and m is less than m plus 1. By transitivity, we have n is less than m plus 1, so case 1 is true for the successor s of m or m plus 1. When n is less than m in the hypothesis, then the case n is less than s of m for inductive step. Next, if n equals m in the hypothesis, then n equals m, and m is less than m plus 1. This gives case 1 for the inductive step, or the successor s of m, or m plus 1. Lastly, m is less than n in the hypothesis. There are two subcases. Subcase 3a, n equals m plus 1. This is the case 2 for s of m. Subcase 3b, n is greater than m plus 1. That is, s of m is less than n. This is the case 3 for s of m or m plus 1. So for each three possibilities of the hypothesis, that is n less than m, then for s of m, we have n is less than s of m. If n equals m, then for s of m, we have n is less than s of m. If n is greater than m, then for s of m, we have either n equals s of m, or s of m is less than n. So, when the proposition holds for m and for any natural number n, it also holds for the successor s of m, or m plus 1. Also, when any one possibility is true, the remaining two possibilities are excluded. So, for any pair of natural numbers m and n, exactly one of the three possible relations or order relations is bound to happen. So, we have established the fundamental property of order relation on the set of natural numbers, called the Law of Trichotomy. From the process of the proof, it is obvious that when we take any pair of natural numbers n and m, they are orderly related. So we conclude that the set of natural numbers, together with this order relation, is a totally ordered set.